All right, folks, it's Bass Action back in action. On this video, we're going to look at both the parts of a pyramid or a cone, and then we're also going to look at a couple examples that help us understand how to make our list, that let's please be happy that I mentioned in the previous video, and how we would calculate the lateral area and the surface area. Now, I have pre-filled out some of the parts on this on this notes page, so you might need to pause and fill some things in as we go along so that you can just process. All right, so starting here at the top, we have the vertex. The vertex of the pyramid or cone is specifically a point where all the lateral faces meet. So the lateral faces, again, are going to be these sides, these triangles. So where all of those meet, we're going to have our vertex. So it would be this point up here at the very, very top. An edge is specifically a segment, okay? It's a segment where the two faces meet. So if we can picture this triangle and this triangle intersecting, this would be an edge. So over here, I have one marked, and I'm going to color it green because I have some physical objects in class, some examples where you can see all these parts, and our edges are green. Now, the edge is not specifically used in any part of our formula, so if I start you with an edge, you will need to do something with it to finally get the parts that you need. The next thing that we're going to have is that slant height. I mentioned the slant height on the previous page, in the previous video, and the slant height is going to be this cursive L, okay? And we can put that in our picture too. The slant height is the height of any lateral face, so it's going to go down the middle of one of our triangles. And the slant heights on my physical objects in class are going to be red. So I'm going to color this one red. Since it's a height, it is going to be perpendicular to that side, and these triangles will be isosceles, which means these two pieces right here will be congruent to each other. Now, the last part that we're going to have is going to be the height of the actual pyramid or cone, and that height is going to be denoted capital H, and it is going to be the distance from that vertex, and it's going to drop straight down, and it's going to land in the middle of the base. So that will be nice and perpendicular. So what we are going to ultimately do is we're going to connect the bottom of the height to the bottom of the slant height, and it's going to make another right triangle. So we've got a couple right triangles that are going to be happening here. Now, if the base of the pyramid that I give you is not a regular polygon, so let's say it's maybe a rectangle, okay? So you can think rectangle here, or maybe even a trapezoid, although we don't do a lot of those, but they could certainly exist, okay? So let's say that I had a rectangle, okay? If it was just a rectangle and not a square, then the only way that you could calculate the area, the surface area, or the lateral area would be to do all the individual faces just like you did when you were in middle school and elementary school. However, if it is a regular polygon, okay, so if it is regular, then we are going to have a little formula that we can develop. Now, let's take a look at this formula. It's similar to what we did for our circle. So what we're going to do, since we're lateral area, just like before, will be the area not including the base, so not including that bottom. We're going to imagine on this one that I have these four triangles here. And I've rewritten those four triangles. I made two of them facing up and two of them facing down. So imagine this is two of them, and they're going to face up, and then the other two would fit down. When I look at this, what I can see is that if I wanted to calculate the area of this now parallelogram, I could draw in this height, and that would be the slant height because it's the height of any of the lateral faces. And of course, then this length along the side, the base of my parallelogram, is only half the perimeter of that, half the perimeter of the base of that pyramid. So the lateral area for a pyramid can be expressed as 1/2 the perimeter times the slant height, okay? Now, let's look at some examples. And again, I did pre-fill this out, so you might want to pause and write all this down, and then I'm going to add some things and kind of talk through it. So let's look at our first one. We have a cone on this one. Now, the base of the cone will always be this circle. it's important to recognize that cones don't have lateral faces. They don't have any flat sides. So when you see this 20 that's along this edge right here, that's not an edge, that is automatically a slant height, okay? On the cones, that will automatically be a slant height. Now, the perimeter of our base, we have to remember that perimeter, okay, the perimeter of our base is, for a circle, is circumference. So if I've given you the whole diameter is 9, then the perimeter of that base is 9 pi. Now the area of the base, remember, we do not want to convert to decimals. So what we probably want to do is write out here to the side that the radius of this base is 9/2, so that when I come over here and I calculate the area of the base, I'm doing my radius squared, which means I square the top and I square the bottom, write it as a nice single expression, gives me that 81 pi over 4. The height of this cone is going to be, it's going to come right here in the middle. So I'm going to draw this in. It's going to make a nice right triangle, and that's going to be my h. And of course, the other side of that right triangle is that radius. So what you can see here is I've set up this Pythagorean theorem. The hypotenuse of that right triangle is that slant height. I have one side of the right triangle is the 9/2, and then the other side is the height, the other leg. Now, working with this Pythagorean theorem, if I square this, that gives me that 81 over 4, and I'm going to subtract it. So that gives me this expression. Now, I'm not quite done with this because I need to be able to solve for the h, so I'm going to put this over 1. I'm going to multiply top and bottom by 4 to get my common denominators, and that's going to give me 1,519 over 4. When I actually take the square root of each side, I would do the square root, and the square root, and that would give me my final height of the square root of 1,519 over 2. It's really ugly, but it works, and most of ours won't look quite like that, but it's good to get comfortable with it. So if I wanted to actually come over and calculate the lateral area of this cone, I would now then pull from my list. I would be able to say 1/2. The perimeter of my base is 9 pi over 1. And the slant height is what I want to do, because remember, I'm doing the outside. And when I clean all that up, I get a 90 pi. Okay, and we would probably want to label that, but I'm kind of out of space on my screen here. Now, for the surface area of the solid, I'm going to take that lateral area, and I'm going to add to that one base. So unlike our prisms and our cylinders that had 2, now I only have one base of this 81 pi over 4. Just like we saw in the last chapter, we do want to get common denominators and write it as a single expression. So that means that what I'm really doing here is I have 360 pi plus another 81 pi. So those are actually going to pull together, and I can write this as 441 pi over 4. And we would only ever convert to a decimal if I asked you to. Now, let's take a look at a hexagonal pyramid. Now, I've specifically included this one in the video because the hexagonal pyramids can be hard for students, so I wanted to make sure that you had a good video to be able to go back and reference. So, I've drawn in the slant height. I can recognize that this 3 square root of 47 is a slant height because this is dashed, okay? If you see that dashed line, it is probably going to be your slant height. The edges will not be dashed. So this is going to be my slant, and you can see that I've already put that in my list, okay? Now, I've also given you, we can also quickly calculate the perimeter of the base because the side is 10. I have 6 of them, so I get a nice 60. If I want to calculate the area of the base, what I like to do whenever I have a hexagon is I do a quick little picture of my hexagon, which since the side was 10, I can fill this in as a 5, and then I automatically know from the last chapter that the apothem is 5 radical 3. Got that down. So then the area of my base is going to be 1/2 the apothem times the perimeter, just pulling that from the previous step, gives me 150 radical 3. And then the last one is going to be a little more complicated. We're going to do the height. So I'm going to drop the height in right here, make this a nice perpendicular. I'm going to connect the height to the slant, thus making this nice right triangle here, okay? Now, you might not be able to see it here in the video, but when you get to class, I'll show you an example. When you connect the bottom of the height to the bottom of the slant, that segment is the apothem that you previously calculated. That's where this Pythagorean theorem is coming from. This squaring the 3 square root of 47, that's the hypotenuse, that's that slant. This is one of my legs, and then, of course, the height that I'm trying to find. So I could even put my h on there. When I square this radical and I subtract that one, I am going to get my h value is 3 square root of 48. I'm going to simplify that, which gives me 2 square roots of 87. Now, real quickly, I'm going to jump into the lateral area. This part will go fast. We're going to do 1/2 the perimeter of the base times that slant height of 3 square root of 47 gives us 90 square root of 47. And then the area, surface area, would be that same lateral. We're going to add to that one base because I only have one base, and that one base pulling from my list is 150 square root of 3. I didn't mean to write a 5 there. Let's clean that up before we wrap up this video. And do my 3, and then we are all done. So I know these videos were kind of long. We're going to do a ton of practice, but it's good to have been exposed to these formulas and parts before you come to class.